Welcome to The Explainer. Today we're going to dig into a really simple but honestly profound idea that connects numbers to shapes. We're talking about coordinate geometry, the amazing invention that basically gave every single point in the universe its own unique address.
So, let's start with a problem. Imagine you're trying to meet a friend in a huge park. If you just say, "Hey, I'm by the big tree," well, you might be looking for a while, right? What you really need is a foolproof system, a universal way to give any point in space a precise, totally unmistakable address.
So, to solve that problem, mathematicians came up with a kind of universal map. This brings us to our first section, the Cartesian plane. Think of it as a grid system that works the same for everyone, everywhere. It's the foundation for, well, everything else we're about to talk about.
And here it is, the Cartesian plane. I know, might look simple, just a couple of cross lines, but this grid is one of the most revolutionary ideas in the history of math. Seriously. For centuries, you had algebra over here with its numbers and equations, and geometry over there with its shapes and lines. They were totally separate worlds. This grid, this was the bridge that finally brought them together, a total game changer.
Okay, so this universal map has three key features you gotta know. You've got the horizontal line, right? That's the x-axis. Think of it as your left or right command. Then you have the vertical line, the y-axis, which is your up or down command. And that super important spot right in the middle where they meet, that's the origin. It's our universal starting point, and its address is always 0, 0.
So, we've got our map. Now what?
Well, now we need a language, a consistent, agreed-upon way to actually write down the address for any point we can possibly imagine.
And that language is called the ordered pair. It's always two numbers tucked inside parentheses looking something like x comma y. And I can't stress this enough. The key word here is ordered. It's just like a house number and a street name. The order is everything. The first number always tells you your x direction, your side-to-side move. The second is always your y direction, your up and down move. If you switch them, you end up at a completely different address.
So, let's just boil this down, right? The first number is the x-coordinate. That's your instruction for how far to move horizontally. The second number is the y-coordinate. That one tells you how far to move vertically. Simple as that.
Okay, so how does this work in practice? Let's try to plot the point A with the address 4, 2. It's a super simple recipe. You always start at the origin, at 0, 0. The first number, 4, tells you to move 4 units to the right. Then, right from where you stopped, the second number, 2, tells you to move 2 units straight up.
And there you have it. You marked the spot. On this entire infinite grid, there is only one single location that can be called 4, 2. No confusion, no getting lost, no ambiguity. It's a perfect address.
All right, section 3. Now, plotting one point is cool and all, but where the real magic happens, where this whole system just comes alive, is when we start to plot an entire set of points that all follow the same mathematical rule.
Let's grab a really simple rule from algebra, an equation, y equals negative 2x. Now, I want you to think of this equation as a kind of recipe, or maybe a rule for a club. It tells us that for any point to be part of our special club, its y value has to be exactly negative 2 times its x value.
So with this little recipe, we can start generating a whole list of addresses that are in the club. Like if you pick an x of 0, y becomes 0. So boom, the point 0, 0 is in. If you pick an x of 3, y becomes negative 6. So 3, negative 6 gets an invitation. If x is negative 2, y is 4, so negative 2, 4 is on the list. We could literally do this forever and get an infinite list of points that all obey that one simple rule.
And now for the really incredible part, the payoff. When you take those points we just found, 0, 0, 3, negative 6, negative 2, 4, and you plot them on our grid, they don't just show up as a random spray of dots. Nope, they all line up perfectly. They form a perfect straight line.
And this, right here, is the big idea. This is that fundamental bridge I was talking about. We've just seen how algebra and geometry are two sides of the same coin. Any equation that creates a graph that's a straight line is called a linear equation. The equation is like the DNA, and the line itself is the living, breathing thing it creates.
Okay, so great. Equations can make lines, but not all lines look the same, right? Some are super steep, some are almost flat, some go up, some go down. How can we use math to describe their individual personalities?
Well, it turns out every single straight line has kind of like a personality, and you can describe that personality with just two key traits. The first is its slope.
That's just a single number that tells you exactly how steep it is and whether it's going uphill or downhill. The second is its y-intercept. That one's even easier. It just tells you the line's starting point on that main vertical highway, the y-axis.
You can really see what I mean here. A line with a gentle 45-degree angle has a certain kind of steepness, but a line with a much sharper 130-degree angle is obviously way steeper and it's pointing in a totally different direction. The slope is the one magic number that captures all of that information.
And the y-intercept? Oh, that's even more straightforward. It's just the launch point. It's the exact spot where our line crosses that vertical y-axis. And if you think about it, that's always going to be the point where x is equal to 0.
Okay, last big section here. So we have these two key personality traits, right? Slope and y-intercept. But what if? What if we could pack all of that information into one single master line of code that could describe any straight line in the entire universe?
Well, guess what? We can, and here it is. Y equals mx plus c. This beautiful, elegant little formula is the universal blueprint for any straight line you can think of. In this code, the letter m always stands for the slope, and the letter c always stands for the y-intercept. It's that simple.
Now here's why this is so powerful. You can take any jumbled, messy-looking linear equation, like the one on screen, and with just a little bit of simple algebra, you can rearrange it to fit that master y equals mx plus c format. And once you do, you can just read its personality right off the page. For this line, we can instantly see the slope m is 2/3, and the y-intercept c is 5/3. Instantly decoded.
And there you have it. That's our whole journey in a nutshell. We started with a really basic problem, how to describe a single dot, and we ended up with the master code that governs every single straight line. We have built that bridge between the world of numbers and the world of shapes.
But honestly, we've just scratched the surface. So the final thought I want to leave you with is this. If a simple little equation like y equals mx plus c is the code for a perfectly straight line, what kind of more complex code do you think you need to write to create a circle, or a parabola, or all the other amazing, beautiful curves that we see all around us in the world? And that's where this journey gets really fascinating. Thanks for watching the